In this video, we'll talk about everything you need to know to create your own full stack applications using the Polygon ZK EVM. We'll do this by first following a transaction and seeing what's going on under the hood by seeing the user's perspective of submitting a transaction, how that gets executed, all the way to how it gets included as part of a batch, sent across to Ethereum, and proven using zero-knowledge proofs. Once we cover off how all of this works behind the scenes, we'll then dive into a coding section where we create and deploy a smart contract to the Polygon ZK EVM, all the way from setting up your wallet, getting funds on the layer 2, to shipping your smart contract to a deployed state. And then we'll create a decentralized application built on top of the Polygon ZK EVM that allows your users to connect to the chain as well as call some functions on the smart contract that we just deployed. Before we dive right in though, if you don't care about anything I'm about to say, check out the Polygon ZK EVM Quick Start. If you're already familiar with creating smart contracts, you don't want to learn about any of the details, just chuck in the RPC URL and the chain ID. Everything else you don't need to be concerned with, as ZK EVM is designed to have the exact same experience from a developer standpoint and a user standpoint as Ethereum. So if you are familiar with Ethereum, you don't care about anything else, go ahead and jump into the documentation and grab what you need. Okay, so just to give you some context before we dive in, this is a presentation deck that I've given a couple of times in real life at hackathons and conferences and events. So I've refined it over multiple feedback sessions in multiple countries, and it's one of my most proud pieces of work that I've done so far at Polygon. So I hope you enjoy it. It's been through a couple of iteration cycles of feedback, and based on the questions that I receive, I try to kind of incorporate the answers throughout the presentation as well. So depending on the context of where you're actually watching this, leave any questions that you have in the comments below or in the Discord relevant to whatever you're participating in. But without further ado, let's get started. So the presentation is called Building Full Stack Apps on Polygon ZK EVM. So the reason Polygon ZK EVM needs to even exist today is because Ethereum and all other blockchains face what's called the blockchain trilemma. And the blockchain trilemma is an issue that all blockchains face where they need to kind of choose their strong points between three aspects of blockchains. So the three kind of points of that triangle or the blockchain trilemma are first, scalability, decentralization, and security. So decentralization, security, and scalability, the three aspects of the blockchain trilemma. When we're talking about Ethereum, it has a very strong sense of decentralization and a strong sense of security that we love, and it's been kind of through battle tested years and years of development to become this decentralized and secure blockchain. However, today, Ethereum can only really handle anywhere from 15 to 60 transactions per second, which even today is not enough to support the adoption of blockchain and Web3 technology. It isn't capable of handling high transaction games or applications or even everyday operations that you would want to use the blockchain for. Things like sending your friends Ethereum or minting an NFT from your favorite collection. There's a lot of demand for both developers and users alike to use these unique capabilities that Ethereum unlocks, like demand for decentralized storage that is available in a decentralized manner that can't kind of be controlled by a central entity, and decentralized compute to have your code running on this machine that is capable of executing your code in a decentralized and permissionless manner. So we love Ethereum for its strong sense of security and decentralization, but it really lacks in that third point of the trilemma, which is scalability. And what this leads to, as this kind of diagram over here suggests, is applications are either being pushed away from Ethereum because the capabilities are not enough to handle what they want from their applications or from their games, or Ethereum or blockchain technology as a whole is just not being built on by, let's say, Web 2 companies because they see this and say, well, I don't want my users to be scared to use my application or be pushed away or be limited to even use my app based on gas fees. So today, even to send someone some Ethereum, you're talking about a massive gas fee of anywhere from $10 to a few $100 depending on what transaction you're actually performing. And obviously this is not realistic for everyday operations like social applications or games where you expect your users to pay huge gas fees to every time they want to write something to the blockchain. So we love Ethereum, but even today, it's not capable of handling the amount of transactions that users and developers desire from this network, let alone what we hope to see in the future, where we reach a point of mass adoption of the Web3 ecosystem and blockchain technologies. Imagine how congested this network is going to be when we reach that point. So Polygon ZK EVM was built to address the scalability issues that Ethereum faces in that trilemma, while maintaining the strong sense of decentralization and the strong sense of security that Ethereum has by utilizing that as the base layer for all of the transactions to kind of live on. And we'll talk about what that looks like further down in this deck here. So essentially Polygon ZK EVM was built to maintain the decentralization and security that Ethereum offers while significantly boosting the scalability by orders of magnitude. So we've talked about what Polygon ZK EVM actually is, but maybe we should actually cover what it stands for. So ZK EVM stands for Zero Knowledge Ethereum Virtual Machine. And that doesn't really mean anything, but let's break it down. So ZK means it utilizes zero knowledge proofs somewhere in the system. And the EVM means Ethereum Virtual Machine, which means it's EVM compatible. And this is an important part because EVM compatibility means you can access all of the existing Ethereum community. All of the development process is the same. You just need to change what blockchain you're deploying to, essentially, just change one line of code. The ZK part refers to what's happening under the hood that allows Polygon ZK EVM to say that it inherits the security and decentralization of Ethereum is because it posts all of the information back and uses these zero knowledge proofs, which is just cryptographically proving the computational integrity of the batches of transactions, which is just kind of fancy words for saying, is what got posted actually correct using zero knowledge proofs? If you've ever read anything about a ZK EVM, you might have seen a diagram that looks something like this, where a bunch of transactions go through layer 2 and all of those transactions get batched together, submitted as one transaction to what's called layer 1. And we're going to break down this diagram because while it does give a good summary of what's happening, it leaves out a lot of the details of what gets sent, how this process happens under the hood. And we're going to explore the process of a transaction being submitted to layer 2 all the way to it being proven on layer 1. And this process really happens in 5 steps. So we're going to cover all 5 of these in a kind of logical order here. So the first one is submitting transactions, where users submit their transactions from a wallet or a script or whatever it might be via JSON RPC. Second is accepting those transactions and executing them based on a couple of quick checks that we're going to run to make sure these are actually valid transactions. Then we move into the 3 steps that kind of happen behind the scenes, where we're talking about inheriting the security and inheriting the decentralization of Ethereum by posting all of that information back to Ethereum. So under the hood, behind the scenes, we're going to take all of the executed transactions, batch them all together, send them across to Ethereum. We're then going to do this kind of 2-step process called sequencing of those transactions and then aggregating those sequenced batches of transactions. And we'll talk about what sequencing and aggregating means as we go through these slides. Okay, so step 1 of 5 in this kind of process is actually submitting the transactions. And if you've ever submitted a transaction to Ethereum or even Polygon's proof of stake chain before, you're probably using a wallet like MetaMask wallet or Coinbase wallet, or you're building out your own applications like Ethers.js or Web.js, Web3.js rather, Web3 Pi, whatever you're familiar with, that allows you to submit transactions via what's called JSON RPC to the blockchain. Essentially, is all you're doing is you're saying, hey, this is what I want to execute. Here's the signature and approval to actually execute that from my wallet. This is the exact same for Polygon ZK EVM. This is an important thing. Again, I want to repeat this. All of the development process is the exact same. You can use all of the exact same tools. You can use all of the existing wallets. Everything from both a developer experience perspective and a user experience perspective is identical to what you would expect in Ethereum. There are 2 key benefits to what the Polygon ZK EVM offers over what Ethereum offers though. So in this example screenshot here, I'm sending my friend 0.0001 Ethereum, and clearly I'm not feeling very generous over here, but as you can see, the gas fee associated with this is tiny, right? It's less than a cent in this example of sending Ethereum to my friend here. So compare this to Ethereum, where you'd pay anywhere from 10 to hundreds of dollars, depending on how congested the network is, for this exact same transaction to go through. So the fees are substantially lower on Polygon ZK EVM compared to what you would experience on Ethereum. The other benefit to this is that the speeds these transactions go through is almost instantly, right? So this whole process from clicking this confirm button, going to the network, all of the stuff that we're going to talk about happening under the hood, sending the information about that transaction, whether it got accepted, whether it got rejected, what the result is, back to the user is all going to happen in around 3 to 5 seconds, right? It's going to be very quickly. And this is an expectation that the ZK EVM has, that this is going to go through and come back very quickly for a very small fee. So we're starting quite simple here, where hopefully most of you are familiar with this kind of screen where you execute a transaction, it either gets confirmed or rejected, and you continue using the application. What's happening on this right-hand side of the screen though is kind of high level, right? It's going to this black box of Polygon ZK EVM and coming back. So let's take a closer look by inspecting what's actually going on under that black box here. So that was step one, was submitting transactions. So it's already very familiar, hopefully, to what you've been building if you've ever used an EVM compatible chain before, such as Ethereum. What happens next is step number 2, which is executing these transactions. So when you actually click that confirm button, or when you run the script, or however you're sending these transactions via JSON RPC to the network, it's going to go into a pending transaction pool. So up the top on the right-hand side here, you can see in this big purple circle, all of these transactions are sitting in this purple pending transactions pool. The sequencer, which is essentially you can imagine it as a piece of software running, looks at this pending transaction pool, picks those transactions up, and decides, hey, am I going to execute this or am I going to get rid of these transactions? It does this decision based on some key inspections that it makes about each transaction. So it says things like, hey, can you actually afford this transaction? Is this transaction valid based on if you're calling a smart contract? Does that smart contract exist? Does the function you're trying to call exist? Is this a duplicate transaction that's going to conflict with another transaction that you've submitted? All of these kind of sanity checks it's going to run and make a decision to say, yep, that looks good, I'm going to execute it, or no, that does not look good, I'm going to discard it, and you'll get a rejection message back into your application or in your transaction. Assuming your transaction gets executed and it was valid, this is going to go through a process called broadcasting, where the sequencer broadcasts the information of the executed transactions to all of the nodes on the ZK EVM network. And these nodes are the ones providing the information back to the application to say, hey, here's the new state of whatever information you require. So maybe you minted an NFT. Here's the information about the NFT you minted. Here's in this case, information about what happened when I sent my friend some Ethereum. So this is just covering step 1 and 2, which are the user-facing aspects of the Polygon ZK EVM, which hopefully, as you can imagine, are, if not identical, very similar to what's happening in any other EVM chain, such as Ethereum, right? It goes into the pool, gets picked up, gets executed, gets distributed to the nodes, and you read that information back in your application. So that's step 1 and 2, is submitting the transactions and executing the transactions. So that's 2 steps out of the 5 that we're going to talk about. So we've covered submitting transactions and we've covered executing transactions. So submitting was just sending them, executing them is doing something with them and giving the information back. What we're going to talk about next is what's happening under the hood that enables the security and the decentralization aspects of the Polygon ZK EVM. Before we do that, however, I want to make an important note at this point in time. So everything we've talked about so far is what the user sees and what most users are going to care about when it comes to interacting with the Polygon ZK EVM. Everything that comes next is what's happening behind the scenes, and usually in almost all cases except one specific transaction that a user wants to make, the user doesn't need to necessarily care about what's happening next. Now, the one point where they do need to care about what's happening next is when they want to withdraw funds from the ZK EVM back to Ethereum. Okay, and what that means is in order to pay for these transactions on the layer 2, which is the ZK EVM, the user would have needed to bridge funds across from Ethereum to the layer 2, which takes right now around 10 to 15 minutes for that process on the mainnet beta environment right now. I'm not sure what it's like when you're watching this video, depends when you're watching it, but right now I believe it's around 15 minutes to go from Ethereum to Polygon ZK EVM, and then you can just live on the ZK EVM, having all of the benefits of the fast transaction speeds and the low fees. However, in order to withdraw funds back to Ethereum, let's say you want to make a transaction on Ethereum, you want your funds back across on the layer 1. What that means is the transactions that occurred on layer 2 need to go through this behind the scenes process where we send all of the information back to Ethereum. The Ethereum chain receives all of those transaction data information and proves it using zero knowledge proofs. At that point, once it's been proven to be correct and what happened on the L2 has been verified by L1 on Ethereum, at that point, the user can withdraw their funds out of the L2 and back onto L1. We're going to talk about why that is the case and what process this goes through to enable that withdrawal back on L1. One of the massive benefits to ZK rollups, such as the Polygon ZK EVM, is that they have a significantly faster withdrawal time than optimistic rollups do. So optimistic rollups typically have a 7-day or a 14-day withdrawal period where they open up an opportunity to say, here's fraud proofs or fault proofs that prove transactions were incorrect, that sort of secure the rollup in this manner, and they allow those to be posted for around 7 days. So users are blocked from withdrawing funds for anywhere from 7 days or 14 days or some number of days that the protocol has set. ZK EVM on ZK rollups, it depends however long you take to generate the proof and post and verify that proof on Ethereum. And as I'm recording this today, it takes around an hour for this process to happen. So Polygon ZK EVM is going to generate the proof, post the proof to Ethereum. Ethereum is going to verify the proof. And at that point, around an hour later, at this point in time, we're going to be able to withdraw our funds. So this is a substantially less amount of time than compared to existing solutions like optimistic rollups. Okay, so what we just saw was the sequencer picks up the transactions from the pool and executes them or discards them. The sequencer is also responsible for an important part of what happens behind the scenes, and that leads us into step 3, which is called batching transactions. So the sequencer is going to take all of the transactions that it just executed and actually batch them up together, send them to layer 1. So in this screen here, the sequencer is going to send across batches of transactions to what we're calling layer 1. And if you're a little confused about what layer 1 means, it's essentially Ethereum in this context. So we're actually sending batches of transactions to a smart contract called Polygon ZK EVM on Ethereum. So one aspect of the ZK EVM is literally a smart contract called Polygon ZK EVM deployed on Ethereum. And what happens here in this step 3 of batching transactions is the sequencer says, hey, I've just done executing all of these transactions. Let's send them all up, batch them together, send them across to Ethereum. And it does this by sending it to a smart contract called Polygon ZK EVM. The way that the sequencer does this is by sending it in this format in the middle here called a batch data. So this is a struct, which is just a way of structuring data on Ethereum, or Solidity, which is just a smart contract language for writing EVM smart contracts. What it does is it says, hey, I've got all of these transactions. I need to somehow stick them into this batch data struct here and send them across to L1. So that's how it's doing it. It's taking the transactions, somehow putting them in this format, which is what we're going to talk about next. And L1, or the smart contract deployed to L1, receives them in this format here. But how does the sequencer take the transactions, which have a bunch of fields, right? It has where the transaction came from, who the transaction's going to, what smart contract that transaction calls, what function it calls, all of the information from the transaction somehow needs to be transformed into this batch data field here. The way that it does that is a two-step process. So for now, you can just kind of ignore the bottom three fields, and we're going to focus on this circled field here called transactions. So you'll notice it's a type of bytes, which is called transactions. So somehow we need to take all of that information, right? Where the transaction came from, who it's going to, what smart contract it's calling, and somehow get it into bytes. The way that we do that is this two-step process here. The first step is serialization, and I have in brackets here RLP, which stands for recursive length prefix serialization, which is really just a fancy way of saying take one data format and transform it into another data format. In this case, we're transforming it into bytes. So we take all of the information that we talked about, where the transaction came from, who it's going to, et cetera, transform it using the serialization process into bytes. And then the second step is called concatenation. It's a hard word, concatenation. And that's literally just a fancy word for sticking them together. Right? So it just literally means join all of the transactions that were serialized together. So we're going to first transform them into bytes and then stick all the bytes together. And that's actually what we're sending in this transactions field here. Okay, so to break this down a little bit, we first here have the sequencer who just executed the transactions. Remember, it made those checks, said, yep, that looks good. I'm going to execute that and then broadcast it. So the sequencer has all of the transactions that it executed, and it says to itself, hey, I need to somehow get all of these transactions into this bytes field called transactions here. So again, this is a two-step process. This was serialization and concatenation. So first, it's going to take these transactions, send them to the serialization process here, serializes them into bytes. So you can see here, the executed transaction 1 goes into bytes 1. Executed transaction 2 gets serialized into bytes 2. Executed transaction 3 gets serialized into bytes 3, and et cetera, et cetera. This can happen for as many transactions as it needs to and can fit into this transactions field here. So it gets serialized into bytes, and now we have a bunch of bytes representing the transactions. And the second step, if you remember, was concatenation, which literally, again, just means stick them all together. So it takes all of these bytes for bytes 1, bytes 2, bytes 3, bytes 4, and sticks them all together. So we have one big long byte of all the transactions going into this transactions field. So I know it's kind of scary when you look at it at first, but when you break it down, it's actually not that scary, right? It's kind of simple what's actually happening. It just says, here's the transactions, let me get them in a format that I can understand, and then I'm just gonna stick them all together so that we can fit lots of transactions in this one field. What's actually happening now is we're going to do this as many times as we need to cram as many batches as we can and send over to L1. This is because it costs us gas fees to call the smart contract on Ethereum, right? The Polygon Z EVM smart contract, it actually costs us gas fees to call that transaction. So we want to get as many transactions as we can into that one transaction. So this process that we just went through is going to happen as many times as we can to cram as many transactions as we can and send as many batches as we can in one transaction so that we get kind of that maximized efficiency when we make that call that costs us money. So we're going to repeat the process that we just saw in the previous slide to make multiple batches, each having their own transactions field. So this brings us to step 4, which is sequencing the batches of transactions. So we just batched everything together, right? And we need to send them to Ethereum. So this is literally all we're doing. We're calling a function on the Polygon ZK EVM smart contract stored on Ethereum. And that function is called sequence batches. So as you can see in the bottom right here, it's probably kind of small. Don't worry, we're going to zoom in the next slide. So if you can't see exactly what's going on, we'll zoom in exactly one slide's time. So what's happening here is on the right side, you can see the transaction is coming from the sequencer, which is the party that we just saw do all of this batching. And the sequencer says, hey, Polygon ZK EVM smart contract, which is the smart contract stored on Ethereum. I want you to know about all of these transactions that I just executed. And I've batched them all up together and tried to serialize them together so that you can understand them. And I've crammed as many as I can so that I made this efficient for myself and kind of cost optimized. So it literally just calls a function called sequence batches and sends over all the batches. So again, it's kind of intimidating at first, but when you look at what's actually happening, it's just sending all of the transactions in a format that is optimized or cost efficient, right? I've crammed them all together into this function so that you know about all of the transactions and you can store them on Ethereum. And this is important because we want all of the transaction data to be stored on Ethereum, because that's how we can say, hey, Ethereum knows about all of the transactions, and what's going to happen next is Ethereum is actually going to verify that these transactions are correct. So if we zoom in on what's happening here, you can see in this case, if I move my head over here, you can see the number of batches that got submitted is actually 52. So that's what I'm pointing at here. In this particular example transaction, we're literally just sending 52 batches of transactions. So if we go back a couple of slides here, we did this process 52 times, right? So I'll move my head over here. We did this process to create 52 batch data structs. Now, important distinction here is that's not 52 transactions, right? Because if you remember, we crammed as many transactions as we could into this transactions field. So we've got many transactions into that field. And then we've also created many batches of transactions. So each batch contains multiple transactions. If we go back to this slide, in this particular example transaction that I've pulled, this sequence batches call had 52 batches, 52 batches of transactions. So it took 52 batches containing multiple transactions each and sent them across to Ethereum. Now, what's happening here is each of those batches, if you can see here, that is literally transactions serialized and stuck together. So that is underlined. It's multiple transactions stuck together. And we repeated that 52 times to create multiple batches, each containing multiple transactions, sent them across to Ethereum. So it looks kind of scary, I will admit, in this slide with all the numbers and letters here. But again, all that's happening is we said, hey, here's what I saw occur on the L2. I've tried to optimize them and stick them all together in a format that you understand on Ethereum, sent them across, and now you know about all of the transactions that I knew about on L2. So this process has taken away so much load off of Ethereum, because rather than users sending each individual transaction to Ethereum, it's occurring on layer 2, and tens or hundreds or thousands or however many transactions that the L2 took care of just sticks them all together in one transaction and says, here you go, Ethereum, here's all of the transactions that occurred. So this can scale Ethereum by orders of magnitude by taking all the heavy lifting away from Ethereum, all the execution away from Ethereum, and just saying, here's heaps of transactions that I know about, send them across to Ethereum. And what we're going to do next is Ethereum's going to say, okay, you sent me all of this, but how do I know it's correct? And that's what we're going to talk about next. Once all of these transactions hit the L1 smart contract from that sequence batches function, we reach the second phase out of 3 phases of finality that the transactions go through in this ZK EVM. So right now we're in a virtual state. And a virtual state just means, hey, I've actually received all of the transactions that you sent to me. And now what I'm going to go do is actually try and prove that these transactions are correct. So if we go to the next slide here, after we submitted the transactions and executed them and went through that broadcasting process to distribute all of that information to the ZK EVM nodes, we were in what's called a trusted state. And the way that I like to think of trusted state is if you trust what the L2 or Polygon ZK EVM in this case, if you trust the information coming back from that, such as the transaction data or transaction history or anything that really occurred on the L2, if you trust that environment, then you can kind of rely on that trusted state, right? So that's kind of how I map the first phase is, hey, do I trust what's being given to me on L2? Then I'm in the trusted state, right? So the trusted state really just means the transactions were submitted and transactions were executed, and we completed the 2 steps out of the 5 steps that we're going to describe throughout this presentation. So what we just saw after the transactions were executed was the transactions were batched up together and then sequenced, which really just means send those batches over to the Ethereum smart contract stored on Ethereum. So the Polygon ZK EVM smart contract stored on Ethereum. And that is where we are now. So as you can see, we're in a virtual state. And the way that I think of a virtual state is we've received all of these batches of transactions, but that doesn't mean they're necessarily mathematically proven to be correct, which is what we're about to do. We're about to use zero knowledge proofs to actually use maths to prove the computational integrity of the batches that got sent and stored on that L1 smart contract. So then once we prove those transactions are valid, we're going to reach that consolidated state. So the first two steps, submission and execution, reaches the trusted state. The third and fourth steps reached the virtual state, which was batching transactions together and sequencing those batches on the L1 smart contract. The fifth step that we're going to talk about is aggregation of those sequence batches. As you can see on the right-hand side, once we aggregate those batches, which we'll see what that means in a second, we're going to reach the consolidated state. And if you remember what we were talking about earlier, where we were talking about withdrawals from L2 to L1, a consolidated state is what's required for us to actually enable those withdrawals. So what we're going to do next is we're going to take the batches that got submitted and we're going to prove them using zero knowledge proofs and reach this point. So that brings us to aggregation, which is step number 5 of this full process here. So we're going to introduce this new kind of party here, which is aggregator. Now, the aggregator's role is to take the batches of transactions that were available on the Ethereum smart contract, and it's going to try to prove that those transactions are valid and post that proof back to the Ethereum smart contract, and the Ethereum smart contract is going to verify whether that proof is valid or not, and then we can reach the consolidated state. And the role of the aggregator is to take these batches of transactions. It says, hey, Polygon ZK EVM smart contract on Ethereum L1. I see you've got these batches for me. I'm going to take them as input and I'm going to generate a proof for you that I'm going to send back for you to verify. So the aggregator takes the batches, sends them to what's called a ZK prover. And as the name suggests, the ZK prover is going to generate zero knowledge proofs, or ZK proofs, that the aggregator is going to receive in return for those batches. And I'm going to kind of oversimplify this right-hand side of the diagram, as I don't really want to go too deep into how these actual zero knowledge proofs work. It's probably a topic for another time. But the ZK prover essentially generates one kind of zero knowledge proof called a ZK stock, which stands for zero knowledge, scalable, transparent argument of knowledge. And this is kind of a bigger style of zero knowledge proof, and it's going to do that multiple times, and then it's going to reach the Snark builder, which is a smaller kind of zero knowledge proof. And this stands for ZK succinct non-interactive argument of knowledge. So that is what's going to be received by the aggregator. And all you really need to know here is it's going to generate multiple big zero knowledge proofs, and then it's going to generate a final proof. And that proof actually proves the other proof. Okay, so it's a proof of a proof is essentially what the aggregator receives. And that zero knowledge proof is small because we want to save as much gas costs as we can when we're sending that zero knowledge proof to the Ethereum smart contract, because again, we're going to pay the gas fee to send this information to be verified. So if you didn't really understand what was going on in that slide, it's okay. I didn't understand it at first either. But the aggregator is sending the Polygon ZK EVM smart contract a zero knowledge proof, otherwise known as a validity proof. So I've been saying whether these batches are valid quite a bit in the kind of previous sections. And the reason for that is because, and the validity proof just proves whether or not the batches of transactions that got submitted in the previous step in the sequencing of batches of transactions, whether those sequence batches are actually valid. The way that it does this, again, I've taken some code from the actual smart contract in the middle here, just so we can see how this actually works. The aggregator is calling a function called verify batches. And within that function, it literally provides the zero knowledge proof that it just received from the ZK prover and sends it as part of the arguments to this function. So verify batches trusted aggregator. Again, the aggregator is the one calling this function. Currently, it's what's called the trusted aggregator, and that is being sent over to the Polygon ZK EVM. So again, here's an example transaction. Up top, we have the aggregator calling the ZK EVM smart contract again. This time it's calling the verify batches function and actually providing the proof here to say, hey, here's the proof of the batches. I want you to go ahead and verify that. And this slide is actually very important, even though it's very small. This is probably one of my favorite slides in the deck, is because this is code taken from the smart contract deployed to Ethereum. And this is what I love about it, is because here's why we can say we inherit the decentralization and the security of Ethereum, because Ethereum, the smart contract on Ethereum, is the one calling this verify proof function. So Ethereum's environment takes the proof, calls verify proof, which calls this rollup verifier smart contract, which basically is just responsible for saying, hey, is this proof legit or not? And says, if the proof is valid from this verification process, then I'm going to reach that consolidated state. If it's not, then we're going to revert, which in Solidity just means kind of get out of that and stop running this function. So that means if it's not verified as valid, then we're going to exit out of the call, and the state of the chain is not going to accept that proof, and the batches that got submitted are not proven yet. So we're still in that virtual state because they are not actually verified to be able to say, hey, this Ethereum agrees this proof that we just received from the aggregator. Something's fishy about it. Something went wrong. Some of the transactions within it are not correct. Maybe someone's trying to do something malicious. Someone's trying to attack this system. All kinds of things could be prevented by running this function on Ethereum. And that's what I love about this slide. So here I'm just highlighting, and it's not that relevant for this particular deck, but here I'm just highlighting why we're using the snark instead of a different kind of zero knowledge proof. So the snark is more succinct, and which just really just means it's smaller than other kinds of zero knowledge proofs, and it costs around 350,000. I believe it's actually less now, gas, to run the function that actually verifies the proof that got sent across by the aggregator. Okay, so now we've covered how the ZK EVM works. We're going to talk about how you can actually build your full stack applications on the ZK EVM. And this part's actually quite simple. Hopefully, if I've got the point across here and done a good presentation, you might have remembered this process of deploying to the ZK EVM is designed to be exactly the same as Ethereum or any other EVM chain. And that means if you've ever deployed to Ethereum, or if you've ever deployed to any EVM chain such as Polygon, POS, then you have all of the skills necessary as both a user and a developer to build the same applications using the same tools, same processes that you're familiar with onto the ZK EVM. You just need to change one thing, which is where you're actually pointing to deploy those smart contracts to. The first process is to actually bridge funds from layer 1 to layer 2. So the bridging process is essentially saying, I want my ETH from Ethereum to be sent across to the Polygon ZK EVM. And this is a simple process. It's even more simple if you're working in a testing environment or a testnet environment. So if you are in a testnet environment, you can go to this website, faucet.polygon.technology, where you can select the ZK EVM tab here, paste your wallet address in, and we'll send you some funds to test with on the ZK EVM for free. So that's probably the easiest way if you're testing. If you are not in a testing environment and you're on the mainnet environment, you can go to wallet.polygon.technology. You can get all of these links from the documentation. Again, please make sure you're interacting with the correct URL. Don't trust any other bridges or websites that you don't know for sure are going to be safe. Please stay safe out there and use the recommended tools from the Polygon documentation. So once you're here, you can select a native bridge and sign in with your wallet, and that is going to take you to the page where you'll be able to bridge your funds from Ethereum to the Polygon ZK EVM mainnet environment. So this is only relevant if you're deploying to Polygon ZK EVM mainnet. If you're on a testnet, you can jump into the faucet, which is available at faucet.polygon.technology, and you'll get some funds on the Polygon ZK EVM for free just by pasting your wallet address into that faucet. And I also love this slide because it shows how simple it is to actually just swap your development environment from Ethereum to the Polygon EVM just by changing the URL that you're pointing to. So if you've ever deployed your smart contracts with Hardhat or Foundry, whatever you use to deploy your smart contracts, just change the RPC that you're deploying to from Ethereum or from whatever chain to the Polygon ZK EVM RPC, which again is available on the ZK EVM documentation, or as I showed at the very start of the video as well. So that's really all you need to do. What I'm going to show you next is creating full stack applications using a framework that I've actually built out called EVM Kit. So EVM Kit allows you to create full stack applications. Here is the website evmkit.com. Here's a quick little demo for what capabilities and features it has built in it. You can connect your wallets with this nice, pretty UI. You can interact with smart contracts on any EVM chain, including the Polygon ZK EVM, where you can read and write information with loading states and error states, everything that you need with built-in PCs, built-in wallet connection, user authentication, decentralized storage, and all of the pieces and parts of the puzzle that you need for the smart contract development side, which is a Hardhat environment. So we're going to deploy a smart contract from within a Hardhat environment, and then we're going to connect to the Polygon ZK EVM, and we're going to connect to our smart contract and start reading and writing information from our front-end environment here. And this is built with Next.js. It's powered by ThirdWeb for both the smart contract development environment and the front-end development environment. And it uses ShadCN UI library for these kind of pretty designs on the front end. So I'm just going to follow the EVM Kit documentation. I would recommend that you do the same, or you can just watch me do it as well. So what we're going to do is actually create the project. I'm going to go ahead and copy the npm command to initiate this project here and open up my terminal. I'm going to maximize this so you can see here. Give me 1 second to make it a bit smaller. There we go. So I'm going to jump into a terminal. I'm on Windows using PowerShell. You shouldn't have any issues, whatever terminal you use. If you're on Mac, whatever, I would suggest you install Node.js, npm, yarn, and git. If you face any issues, check your Node version, check you have all of this stuff installed. You shouldn't face really any issues with the CLI though. So just go ahead and copy the install command, paste that into a folder, and replace this My EVM Kit app with a name of your project. I'm just going to say demo EVM Kit app here. And that's actually going to clone a template repository from GitHub and essentially make a copy on your machine. So once this goes through, as you can see, the EVM Kit pops up, and the next suggested step is to change directories into that folder. I'll just go ahead and clear it up. So the next step is to get a ThirdWeb API key. So ThirdWeb allows you to utilize their free kind of RPC services. So we're going to go ahead and get an API key, which is free, at least for a specific amount of usage. And then we're going to plug that API key into our application. While we do that in the background, what I'm going to do is open this up in my text editor by typing code dot. And what I'm going to do is open up a terminal in VS Code. And I'm going to click this split icon over here, just on the very right-hand side. Hopefully you can see that. I'm going to split it. And then from the left-hand side, if we open up the folders section here, you can see it's kind of split up into two sections. So there's application and there's contracts. We're going to change one terminal into application, which is our front-end environment. And we're going to change another terminal on the right-hand side here into the contracts directory. So cd contracts, I'm just going to zoom out once here so I can stop leaning over here. And then both terminals, we're going to install the dependencies. So you can use npm install, you can use yarn, you can use pnpm, whatever you prefer. I'm just going to use yarn because that's what I'm most familiar with. So I'm just going to type yarn in here. I'm going to type yarn into the contracts section as well. So while that's happening in the background, I'm going to head over to ThirdWeb. So this is just at thirdweb.com. What we're going to do is click get started here, and we'll go into this top right corner. I'll just put this into frame for you. And what we're going to do is we're going to connect our wallet and connect with whatever you want. I'm going to use MetaMask just because I have some existing test funds available in that wallet. I'm going to sign in, go ahead and sign the message from my wallet as well. And we're going to go and head over to the settings section. And you can see here, we're going to create an API key. So click create API key, just give it a name. Let's say demo EVM Kit app. And I'm just going to go ahead and select everything with unrestricted access. You can pick and choose which services you want. Really, you don't need to concern yourself that much. Just go ahead and create one for testing purposes, get yourself up and running. So I'm just going to say unrestricted access, tick everything off, click next, unrestricted access again, and create it. So this is going to present you with your client ID and your secret key. I'm just going to leak mine here because I don't really care if you use these keys. Maybe I'll blur it out in post-production. You, however, should keep them safe, especially if you are going to use the paid services that ThirdWeb offers. You should definitely keep these safe. But what we're going to do is I'm going to copy this one and I'm going to go into the application section. And in the application section, you'll find a .env.example file. What I'm going to do is I'm just going to copy and paste this, rename the copy and pasted file to .env. So this is kind of our secrets file. You'll see it gets grayed out, so you don't commit this to GitHub or any kind of leaks into wherever you're storing your code. You'll see up the top here, there's a field for a public ThirdWeb key and a ThirdWeb secret key. So let's go ahead and go to grab our client ID for the public key, and the secret key is this key here. I'll paste that into the ThirdWeb secret key field. We don't really need to worry about any of the rest for now. That is going to take us to the next step. So we'll go to the getting started section, and that's really it. So if we open up our terminals again here, let's just open that back up. You might see this is running something on the left-hand side in the application. I'm just going to go ahead and kill that process because I don't really care about the ThirdWeb generate in this particular scenario. So I'm just going to kill it and I'm going to clear both of these. And what we're going to focus on next is actually the smart contract development section and deploy our smart contracts to the Polygon ZK EVM. So what I'll do is open up this contract section here. You'll see now we have the yarn lock file, which if you see this, or if you see a package lock.json file, that means your dependencies have successfully installed. Within the contracts folder, there's another contracts folder called greeter, where a file called greeter.sol is available. You can see here is just a very basic smart contract, which has a constructor, a read function and a write function with some emission of events as well as this internal state. So all we're really doing is storing a value called greeting in a variable called greeting. It has a constructor where we can provide the initial value of that greeting. It has a read function to actually read the value of the greeting and a set greeting function to actually write or update the value of the greeting, which is going to require us to initiate a transaction and pay some gas fees. And it's going to emit this event called greeting changed, which is defined on line 25 down the bottom here. So you can change this to whatever Solidity smart contract logic you want. I'm happy with the greeter smart contract I have. What I'm going to do now is show you how to deploy this to the Polygon ZK EVM network. So what I'm going to do is, if you just keep your terminals open, from the contracts directory here, so you should be within contracts. If you're not, just say cd contracts. Don't do that too many times, though you might get lost, but just make sure you're in the contracts directory before you run this command. So what we're going to do is, if you open up package.json, you don't have to do this. I'm just going to show you what's going on. You'll see there's a script called deploy. So what this does is, it's actually just going to take the smart contracts and it's going to open up a UI via ThirdWeb dashboard for us to actually deploy these smart contracts. So what we're going to do is just going to run yarn deploy from, again, within that contracts directory here. This is going to run the underlying ThirdWeb deploy command. You might be prompted to update your ThirdWeb package. Just go ahead and accept that. And you should see the ThirdWeb logo come up. It detects that you're running a hard hat setup here. What it's going to do then is you'll see it's compiling. If you really want to look at what's going on under the hood, you'll see the artifacts and the cache folders pop up. Within the artifacts folder, you can see, okay, here's actually the greeter.json. And if we scroll within this file, you can see the ABI get output. You can see the bytecode. You can see the deployed bytecode. What we really care about, though, is this URL here. So you can see the process was successful, the upload was successful. So that means our contract is ready to deploy via this URL here. So let's go ahead and open this up. And this is going to take us to the deployment page. So you can select any EVM chain you want here, including Ethereum, Ethereum testnets, Polygon, POS chain, Polygon proof of stake chain, a testnet, like the Mumbai chain. Really, any EVM chain is available here. And what we're going to do is just define a initial value for our greeting. So these are fields that get dynamically created kind of based on your constructor. So whatever arguments you need to provide to your constructor will be available as options within this field here. What we're going to do next is down here, we're going to select the Polygon EVM, so search that up. And you can see there's Polygon ZK EVM, there's Polygon ZK EVM testnet, there's also the Polygon mainnet, and there's also Mumbai if you want to deploy to the proof of stake chains, as well as any of the CDK chains should also be available here. If you can't find it, you can add a custom network where you can provide your own RPC, your own chain ID, all of the information required. So what I'm going to do is I'm going to go to the Polygon ZK EVM testnet. I'm going to select that, which will prompt me to first add the network to my wallet and then swap over to that added network. Since I've already got it, it's just one step to swap over. If you don't have any funds, you'll be able to see in your wallet up the top right here. If you don't have any funds on this network, that's where the faucet comes in. Or if you're on a mainnet environment, that's where this bridge comes in here. So if you're in a testnet environment, all you'll need to do is log in with Discord to make sure you're not a bot farming the faucet, and paste your wallet address in, which you can copy from this copy address icon here. Receive free Ethereum testnet funds on the ZK EVM to test with. Just make sure you've got this tab selected of Polygon ZK EVM here. So since I've already got some funds on the test network, all I need to do is you can add it to your dashboard if you want to visit it later. I'm just going to skip that step, move my head over a little bit so you can see. I'm going to click this big deploy button here. So go ahead and click deploy now. This is going to prompt a transaction in your wallet here. Contract deployment, you can see very, very small gas fees, which we love to see. One of the massive benefits of the ZK EVM testnet. Go ahead and click confirm. The second major benefit is, wow, that transaction went through very quickly. A matter of seconds to actually process that transaction and receive the updated information of the chain comes back in a matter of seconds. So now we've just deployed our smart contract successfully onto the ZK EVM testnet. So that's the smart contract development side of the full stack development setup. What we're going to do next is we're going to jump into the application, and the application side of the EVM kit is built using Next.js and the ThirdWeb React SDK, among a variety of other tools like ShadCN UI, which is an amazing UI library. I think you're going to love it if you haven't seen it already. So what we're going to do now is we're going to take this smart contract that we just deployed, and we're going to plug it into our front end to allow users to connect their wallet, swap on over to the ZK EVM, and then actually read and write information from this smart contract here. So let's jump into the application folder now. Head back on over to the code window here. And what I'm going to do, since we're done with the contracts folder here, I'm just going to close that side of the terminal, leave the application terminal open. And what we're going to do now is let's actually just open that up into our code editor here. So we'll get rid of all of the stuff that we're not using anymore. And within here, you can see a couple of different things. You should first see this, where is it? Yarn lock file or package lock or PNPM lock, whatever you're using, you should see this. If you don't see one of those files, that means you need to install the dependencies first. Please make sure you have done that. Otherwise, it's not going to work. So you should also see the .env. Please keep this secret. Unlike I'm doing here, I don't care about these secret keys because I don't have any funds that I want to keep safe, or I'm not using any of the paid features, at least from this account on the ThirdWeb dashboard. So please keep these safe. You should never ever leak any of your values. Please do not follow what I'm doing. If I haven't bothered to blur it out, I'm lazy, but I don't care if you use these keys. There's nothing being lost for me, but you should never ever let anyone see these or use any of the keys. Okay, so please be careful with this file. What we're going to do now is inside of the application folder, there's two kind of configuration files in the const folder. So one is called chains, and chains allows you to define two chains that your application is going to work on. The chains file, allows you to define a development chain which is just set to Mumbai, and also allows you to define a production chain, which is again just set to Mumbai. The way that this works is it exports this variable here that says, is this a development environment? If it is, then we're going to use the development chain. If it's not, i.e. it's one of your deployment URLs, we're going to use this production chain value, which in this case, are just both set to the same thing just for simplicity. But what we're going to do is we're going to change this from Polygon Mumbai to the Polygon ZK EVM testnet. So go ahead and import that from the @TheWebDev/chains package. I'm just going to get rid of both of these and set our development chain to the testnet. Also going to set our production chain to the Polygon ZK EVM testnet. So now we've declared to our application to say, hey, this is actually the chain that I want to use for both development environment and a production environment. The second configuration file is this contracts file. And this actually works pretty similar. So it first imports that, is this a development environment variable from the previous file that we just looked at? And it then allows you to define two smart contract addresses. One that says, hey, here's a smart contract address on the testnet that I'm using. And the other one says, hey, here's the smart contract address that I'm using on the production chain. So for us, what we're going to do is, since we're on the Polygon ZK EVM testnet for both our development environment and production environment, let's go ahead and copy the address of the smart contract, which is available at this button here. Then what we're going to do is we're going to replace that value with the smart contract address. And just for good measure, if we want to deploy our application, let's just paste that into this value here as well. And you can repeat this process for as many smart contracts as you want, and repeat this kind of process for as many smart contracts as you want as well. I think most cases you're just going to use one or two development environments, one for development and one for production. If that's not the case, you can completely not use this file if you want to. It's really up to you how customized you want this setup. So the way that that works is in the TheWeb provider, in this app file here, which wraps our whole application, it's going to set the active chain to the chain that we import from that chains file. That was a lot of chains, but essentially it says, hey, is this a development environment? Read this chain. Or hey, this is a production environment. Read this chain and operate on that. Okay, so hopefully that makes sense. Then in the index file, we have a couple of different components that we're just showing off. You can pretty much safely go ahead and delete all of this stuff. So let's go ahead and delete this, delete the tabs. I just don't want any of the demo. Let's go ahead and delete the state and delete any of this kind of extra stuff that I don't care about. So I'm just going to go ahead and delete this. And now we just have this EVM kit section. Let's maybe change that to say hello world and delete this. And now we have a very simple homepage that we can test on our local host. So from the terminal, just go ahead and run yarn dev or npm run dev, whatever package manager you're using. Open up your browser at localhost 3000. What you should see is your application kind of available for you to preview what's actually happening in your code. So while that's happening in the background, you can see this is just loading up using Next.js. Seems like it's ready now. Give it a couple seconds here just to load up for the first time. And here we go. Okay, so we have the header component and then we have our homepage, which just says hello world. So to make it even simpler, let's go ahead and first allow our users to connect their wallet. And then we're secondly going to allow users to read and write information from our smart contract. So the easiest way to do that is use the use contract hook from the TheWeb React SDK. So here's the documentation. You can read through it if you want, but it's pretty similar. If you've ever used WAGMI, it's also very similar. What we're going to do is at the top of the file, we're going to use that use contract hook, deconstruct the contract value out of the use contract hook, import that on line 1 here. And then we're going to say, we need to provide the contract address, okay? And if you remember, we just pasted that in to a value in contracts.ts here. So I have a contract value or variable here called greeter. Down the bottom, it says, hey, am I in a development environment? Then I'm going to use the I'm going to use the value for the dev smart contract. If I'm in a production environment, I'm going to use the value for the production smart contract address here. What we're going to do is we're going to import that value. So we're going to say greeter, and you can see the first option here is for me to import that. On line 3, I'm importing greeter from that, and you can see here is the value that it's importing. Okay, so now we can interact with the smart contract that we have just kind of connected to via this hook. So what we're going to do first is we're going to say read the smart contract greet function. And then second, we're going to actually call the set greeting function using what's called a Web3 button component, the Web3 button component. So what we're going to do here is we're going to use, again, this is very similar to WAGMI. If you've ever used WAGMI before, what we're going to do is we're going to say use contract read in top of the file here. So we're going to import that from the React package. We're going to say, hey, const data. So we're going to deconstruct the data value out of what gets returned from this hook. We're going to say is equal to use contract read. And we're going to first provide that contract here. And you'll see we need the function name as the second one. Now I'm going to show you, since we already know ahead of time, we know that the function is called greet. But what if we typed a typo in here? It doesn't actually know what's kind of going wrong here, right? We can legitimately call this, and TypeScript has no idea, it's not complaining. And that is because we haven't run what's called the generate command. So if you care about type safety, if you care about TypeScript, this is for you. So what we're going to do is we're going to open up the terminal in the application. I'm just going to split it so we can keep running the environment here. From the application directory here, you can see there is a script called generate. And generate is essentially going to read all of the files within your project and say, hey, is there any smart contract addresses that I can fetch the ABIs for so that you can use things like use contract read safely with kind of TypeScript compliance. So what we're going to do, if you care about TypeScript, if you don't, you can probably skip the next minute. What we're going to do is run this generate command. So we're going to run yarn generate from the application folder here. And this is going to run the underlying third web generate command, which is kind of going to go and say, hey, we found an ABI for one of the smart contracts. So it first says, hey, is there any smart contract addresses in here? Looks like there is. There's OXCE. I'm going to go ahead and get that ABI for you. And I'm going to kind of make the ABI available for your TypeScript compiler. So now I'm going to hit Control-Shift-P and search up Control-Shift-P, and search up restart TS server. Click this. And then once this little spinning icon down the bottom here, you can't see it on this screen. If I drag it up, see there's a spinning icon here that is kind of loading up and saying, hey, some stuff's going on. What's going on? We're going to load it up. What we should see is this use contract read starts to say, hey, wait a minute, something's not right here. You don't have a 1, 2, 3 function on your smart contract. Give it a couple more seconds here. While that loads up, I want to show you where this gets stored. So it's pretty cool. It actually stores the ABI inside the node modules folder in the @thirdwebdev/generated ABIs. And in here, you'll be able to see, okay, hey, my OX2E7, which actually doesn't look like the right one. What we care about is OXCED. So copy that. And it doesn't seem to actually be there, which is not what I wanted. Okay. If this kind of bugs out like it is for me, you can go into the ThirdWeb.json folder and you can actually manually replace this. So you can add any contracts in here, set the chain ID. So what I'm going to do is this should ideally for you just pull this stuff automatically. I'm just going to replace this with my smart contract address. And then I'm going to change the chain ID. So the chain ID should be the chain ID of the ZK EVM testnet, which you can actually get from the infrastructure tab here. And you go to RPC, you'll be able to see what RPC the network you're connecting to is using. So in this case, I'm going to search up Polygon ZK EVM testnet here, and you'll see, okay, the chain ID is 1442. So let's go ahead and set that here, Let's rerun that command, yarn generate on the right-hand side here. So yarn generate, the sort of bugged out in the visual, but I'm just rerunning the previous command. It says, hey, here are the new ABIs from that file. Now, if we again run that restart TypeScript server command, it'll initialize down the bottom here to say initializing these features. Give it a couple seconds here. What we should see now, there we go, is it says, hey, wait a minute, you don't have that function on your smart contract. You only have greet or set greeting, so you can't call this. So this prevents you from writing typos or running into any bugs where you just made a silly little mistake and TypeScript's there to kind of help you save the day. It was a little bit of work in the end to actually get that to work. But if you do care about having your TypeScript be helpful in these little read and write operations, it is sometimes worthwhile to actually go through that process. So instead of greet123, we can now see, or you can call either greet or set greeting on your smart contract. So that's what's happening with that generate command. Let's go ahead and hit the greet function. That's what I want to read. And really the benefit to this was essentially now you don't need to copy and paste APIs. Maybe you have one person working on the smart contract. Maybe you have some other people. You need to make new configuration files to store the APIs. You need to make sure you have the API up to date. You can just hit that yarn generate command. It's going to go ahead and fetch the latest API of your smart contract, pull it into a place where you don't need to care about it, and you have type safety on read and write operations. I think it's pretty cool. It was a little janky to get completely set up, I will admit, but hopefully it's worthwhile for you TypeScript lovers out there. So now what we have is we have the data field, which we can go ahead and rename using this colon syntax to say, hey, let's rename this data field to be greeting. So now we have the actual value read from the smart contract in a field called greeting. We can also pull in fields like is loading or is loading error. The actual one that I want is loading. And maybe we can pull in error as well. So this brings in the error message of if something went horribly wrong, you can console log this or inspect what's going on or display an error to the user. I'm just going to go ahead and use the loading field and the error field for the application here. So I'm going to scroll down and beneath our heading here, I'm going to add a p tag that displays the loading state first of all. So if it is loading, I'm going to say display a loading tag. But once the field loads, I'm going to say, let's actually display the greeting. So greeting in a p tag. And if we go back to our localhost, should be able to see, where's my localhost gone? Here it is. Okay, so we should be able to see, very small here, but it is first loading when we refresh, loading until it comes back. And then we display the actual value of the variable on the smart contract. So that's pretty cool. What we're going to do next is we're actually going to update the value on the smart contract as well. We're going to do that using this UI component called a Web3 button. Now the Web3 button is very cool because it first connects your users to their wallet. It secondly swaps them over to the network that you've defined. And finally, it actually allows users to click the button, call the function on the smart contract, has a nice loading animation while we wait for that transaction to go through, and then updates any of the read values that we have automatically. So, whoops, that's the wrong button. What we're going to do next is we're going to, beneath this p tag, we're going to add a Web3 button. So just type out Web3 button, go ahead and select this, import it from the React package up the top here. Make sure that's there. And then we first need to grab the contract address. So there's two fields we need here. First is contract address, and the second is action. And then we can close that off, put the text here to say whatever you want. Let's just say set greeting in this case. Here, we're going to use the value of greeter. So let's just paste the contract address is greeter. Again, that's going to use the development contract address in the development environment and the production contract address in the production environment on the correct chain. Within the action here, we can access the contract and we can simply just call contract.call. And we're going to type the set greeting. What have we got here? Set greeting. Not sure why the TypeScript is not popping up. Call the set greeting function. And then we need to provide in an array here the new argument that we want. So let's just say new value. You can alternatively use this use contract write value if you want the type safety. So you can say mutate or mutate async if you prefer working asynchronously, and deconstruct that out of the use contract write hook. Again, you'll need to import that on line 1. Then you should get the type safety if you pass a contract. And then if you hit, yeah, there we go. So you can get greet or set greeting. In this case, let's use the mutate async. And instead of this way, just so I can show you the type safe way as well, what we're going to do is we're going to call this mutate async function, which again, we can rename to be set greeting. Save that. So now we have a function called set greeting, which calls the set greeting function on the smart contract. Hopefully that's self-explanatory. Within the action, we're going to call this function and say set greeting. And here we need to provide a object, and arguments are set to an array of string. So if you provide something that doesn't work here, it's going to tell you off. With the TypeScript set up, if you provide a valid value such as hello world, this is a new value, set that in here. What we're going to do is actually go back to our application and preview this kind of setup now. So if we click this, first, it's going to pop up with this really beautiful customizable Connect Wallet component. Go ahead and connect our wallet. It's going to swap us if we're on the wrong network here. For example, if I swap to Ethereum mainnet, it's then going to say switch network and confirm that in your wallet. Swap us over to the network and then show the actual button. So now we can actually call the function. This is going to load up and be disabled while it is loading up. Go ahead and confirm this. Spins until that transaction goes through. Should be a couple seconds here. Should be like 3, 2, 1. Here we go. Couple seconds. There we go. It's gone through. And the transaction, as you can see here, has automatically updated based on that function being called. So this is pretty handy. The values automatically update. The button is disabled while it's loading. The user is easily onboarded to whatever chain you're using, and it gets some pretty nice designed UI components here as well. So that brings us to the conclusion of full stack development on the Polygon ZK EVM. If you're interested in using the EVM kit, if you like the way it looks, I'd recommend you read through all of the other capabilities that come kind of out of the box. My favorite one is the Shadcn UI capabilities with his CLI that he's built. He recently joined the Vercel team. Amazing library. Would definitely recommend you use this for your front-end development if you're interested. All of the other features such as decentralized storage with IPFS, user authentication with the sign-in with Ethereum standard, really taking ThirdWeb's capabilities to its limits here in this EVM kit, and a lot of cool stuff that you can do and kind of get up and running very quickly. Hopefully, if you like it, you can join the Discord as well to ask any questions that you might have. And again, it is all completely open source, so if you want to contribute as well, feel free to do so. I also have another video on my channel about EVM Kit as well. I believe it'll be called How I'm Building Web3 Apps in 2023 or in 2024, whenever you're watching the video. Hopefully I've remembered to update the title. The video goes into a bit more detail than I did here, but hopefully that was a good introduction to creating full stack applications. Again, the massive benefit to a EVM compatible zero knowledge rollup is that you get all of the familiarity with both dev tools and user tools out of the box as it is EVM compatible. So it's a massive benefit to be EVM compatible, use all of the familiar tools, all of the familiar wallets to actually create these applications. And really all you're getting is a much more scalable chain that you can build on. So that's it for this video. Remember to leave a like if you enjoyed it, subscribe to the channel if you want to see more Web3 content very soon. And if you did, I'll see you in the next one.